lecture of this course. I hope you have enjoyed this so far. So we will today continue with scalability and MapReduce. I know it was a little bit hurried yesterday, but today I'm going to show an application of MapReduce and from a recent paper. And also I'm going to show the dashboard we have developed for graph analysis using multi-layer networks and life cycle. So this is what I'm going to present today: designing efficient and scalable substructure discovery algorithms for multi-layer networks. So this thesis was completed by Arshdeep Singh maybe 3 semesters ago, and Abhishek and myself. It happens that Arshdeep Singh is from Amritsar. He told me there is some Guru Nanak University or college. He is from there. So he did his master's thesis and has taken up a job. He has done a great job, you will see. And this was presented in this year's conference in September. So instead of condensing it, I'm just bringing it as is. So what is the problem? The problem is substructure discovery in MLNs. What has changed? So why are we developing another algorithm for substructure discovery? Because there are already algorithms for substructure discovery, because the graph model has changed. Earlier we were doing it on the simple graph. Now we are doing it on the multi-layer network. Earlier we were doing it as a main memory algorithm. Now we are doing it on the MapReduce framework in order to accomplish scalability. So why develop a new algorithm? None of these algorithms exist for MapReduce, for parallelization, and for scalability. Is this a new algorithm or a different approach? It's both. So it's a new algorithm where we are applying the decoupling approach. Remember, I talked about analysis function and decomposition function. So we have developed a new decomposition function in order to do the substructure discovery based upon decoupling approach. What is the new approach and the algorithm? We'll see. And we also show results and validation, conclusions and future work. So as I have shown earlier and indicated earlier, substructures exist in different ways, in different domains, in different contexts. So this one is an example. I will also show you in the dashboard. So if you take, this is a synthetic example, just to make it clear what a substructure is. In this graph, you can see that A, B, C, D appears twice. So this is a substructure that repeats twice. So this is what we want to find out. We want to find substructures, not only the substructures, but also how many times it repeats. The more it repeats, the better the quality of the substructure is. Now you should also understand this is a large substructure, 1, 2, 3, 4 edges, and the connectivity is same. A to C, same thing here, A to C, so on, and can verify. This also means there's a one edge substructure that is common, 2 edge substructure that is common, 3 edge substructure that is common, and the largest is the 4 edge substructure. Now why do we pay importance to the largest substructure? Because if we were to condense or compress this gap, so for example, if I were to reduce these 4 into one node, these 4 into one node, this graph compresses the best. Whereas if I take a 2 edge substructure and compress, still the number of nodes and edges will be more. So compression is considered as a metric. It is considered as an information theoretic metrics and used for seeing how good the substructure is in terms of compression. So when we want to discover substructures in this graph. We want to discover the maximal substructure in this graph, which is this one colored orange, which appears twice. Now these are real world examples that I've been showing. There are substructures. So if you feed this graph, so you have to just format or convert this graph into the input and run the substructure discovery algorithm, and you will get the best substructure. In the synthetic graph, we know what it is. The reason we do that, we embed these substructures to make sure the algorithm is correct. It is finding what it should find. Once we are sure algorithm is correct, we can run it on any real world data, and we know that the output is correct. So how do we find these systematically and accurately in a very large graph? How do we do it across multi-layer networks, across layers? How do we find the largest one that is meaningful, which compresses the graph most? So that is the problem at hand. So problem statement is to develop an algorithm for mining. We call it interesting substructures that compress the graph very well in a homogeneous multi-layer network. So what is an interesting substructure? Frequent substructure or the one that compresses the graph better. We use the MDL as the metric for compression. You can use other metrics also. So what has changed? Our graph model has changed. That means it adds new challenges. Multi-layer networks instead of single graphs. MLN model, multiple entity types and multiple relationships. Existing algorithms work only on simple graphs. Can we not use the same algorithms for MLs? Not really, but we can use existing algorithms for individual layers. So this is what we saw in the decoupling approach. We can still use the existing algorithms, but add something in addition to compensate for the multi-layer networks. This we have seen earlier, so I won't spend much time on it. So we have a homogeneous multi-layer network, we have a heterogeneous multi-layer network, and we have a hybrid multi-layer network. All this, so when you have an application, we don't know which model is the most appropriate one. So it is the task of the designer or the modeler to determine which of these models are most appropriate for this problem. And that is where the analysis starts, modeling. Because if you don't model your problem correctly, you're not likely to get good results, you're not likely to get correct results. We have also seen different ways to analyze the multi-layer networks. So on the left side, we have the what we call the traditional approach or the aggregated approach, where we collapse all the layers into a single graph and remove the distinctions of the relationships and node types, and then we apply the algorithm and we get the result. So we also saw that in this way of doing it, we may lose some information, both structural and semantic information, so this is not the best way to do that. But however, we can certainly use it as our ground truth, because that's what we want to get. But we also want to preserve the structure, we also want to preserve a semantic. So this is a situation where you want to have your cake and eat it too. So that's what it corresponds to. On the right hand side, we have a different approach where we don't collapse it. We use the MLN assays, but these applications are quite complicated. There are some applications, but they are pretty difficult to develop. So we adapt the middle approach, B, where we use the existing algorithm to do partial analysis, and then we do the composition. So we have two phases, analysis phase and composition phase, and you get the final result as a result of that. So this is from his thesis. So challenge is verifying the correctness of the approach with respect to ground truth. Evaluate the efficiency and scalability of the approach. So this course is more about not only cutting edge analysis, but also scalability. So this is a very good example of how we can accomplish scalability. So the contributions from this thesis are the following. So he proposed two composition algorithms. I'm going to show only one of them in this lecture. The thesis is online. Later I will show it. If you are interested, you can read it. For substructure discovery in a multi-layer network, incorporating the decoupling based algorithms within the MapReduce framework, ensured correctness of both approaches, evaluated the impact of various parameters. Remember, I talked about layer characteristics and graph characteristics. So layer distribution, beam size, substructure size on the accuracy and scalability, extensive experimental analysis using real world and synthetic data. So this is very important. I'll show, I think in his thesis, he has performed about 91 experiments on slightly different 91 data sets. So this is what it takes. So remember, this is a master's thesis. You can compare this to what perhaps your MTech students do for the second year of the project, and you can see, what work has been done and what you do, and see how it compares with each other. So correctness of substructure discovery. So how do we know what is correct and what is not correct? Here is a simple example. Suppose I have this original graph. Now we always take small toy examples that I'm asking you to try and test, because you can verify these manually. If you take a very large graph, very large data set, you don't know whether your result is correct or not. So this is a single algorithm. You see there are two colored edges, blue and orange. Suppose say this is the substructure that is discovered from this graph. So this is what we want to discover as an example. Now suppose you break that original graph into two layers, layer A and layer B. Layer A contains orange edges, layer B contains blue edges, and the goal is we want to get the same output. So this is what we do, what we mean by ground truth and verifying with ground truth. So ground truth is what you get from the original graph. Our algorithm does it in a slightly different way, and the question is whether you still get the same output or you don't get the same output. This determines correctness. So computation along that line, computation along this line should give the same end result. That's when you know your algorithm is correct. Okay, so what is the need for composition? Suppose I have layer 1 and I have layer 2. I run the analysis algorithm. This is the original graph, just to keep things in the context. And this is a substructure that is derived from the original graph. The reason we are showing it in different colored edges, you will see later that blue edges correspond to one layer, orange edges correspond to another layer. So we want to see now, again, I also talk about presentation and how to make people understand. If I just drew all edges in the same color, it will be a little more difficult to understand where it comes from. So if I done the analysis on layer 1, I only get subgraphs of orange edges. If I run the analysis on the layer 2, I only get subgraphs of blue edges, because there are no orange edges in layer 2, there are no blue edges. So I will not get this subgraph if I just do this analysis independently. So this is what you need to understand. That means something is missing. Something is missing because you will not get the substructure which spans across two layers from individual analysis. So what do? So we need to develop an algorithm, the composition function, which takes these things and generates that substructure. So that is the solution. So you take individual substructures from individual layers and then you compose them to generate substructures that are missing for the original graph. Then you get the correct result. So this is the key. This is the key. This composition we talked about, this is the analysis function psi. This is the composition function theta, and without this you cannot get this output, so the individual analysis will not be correct. So this is the crux of the problem. I hope you understand it clearly. If you have any questions, please ask me. So in order to do this, we use something called canonical representation. We use a tuple, a 5-tuple, to represent an edge in a graph. So for example, X is the edge label, number 2 is the source vertex number, A is the source vertex label, 5 is the destination vertex number, B is the destination vertex label. So with this representation, we can represent any graph as single edges. Whether it has 100 edges, 1 million edges, or 10 million edges, does not matter. So you can see now how we can map this to the MapReduce, because now we are going to take, we are going to partition the edges and give different graphs to different mapping nodes, and they process each edge separately and then do some magic in between. So here are, so these are the representation for this graph. So you can verify that edge X has 2 and 5 as source and this vertex, and edge Y has 4 and 5 as source and this. So direction is important, and substructure should also include the direction. You can also do substructure discovery in an undirected graph. Then you don't have to worry about the direction. So here is another graph. So what we are saying is, when we expand the graph, so we start from 1 edge substructures, we generate all 2 edge substructures. From 2 edge substructures, we generate 3 edge substructures, so on and so forth. When we do that, we may generate some duplicates. So we need to identify those duplicates, and in order to identify those duplicates, we need to represent them in a canonical form. So this is a canonical form where the edges are ordered lexicographically by the edge label. So X comes first and Y comes later. If they are same, we order them by the source vertex. If they are same, we order by the destination node vertex, and so on and so forth. So you can see that even though these two look differently, they are identical. So if their canonical representation is the same, we can remove one of them and we don't have to keep both of them. Similarly, in order to identify subgraphs, we also need a slightly different canonical representation, and that is shown here, and that uses a slightly different one where edge node numbers are converted or mapped into a relative ordering. So for example, in this example, node 2 in this one is mapped to 1, 5 is mapped to 2, 4 is mapped to 3, and then when you do that, you get a representation in which both of them are identical. So we can say these are isomorphs or exact matches. So again, you can do the same thing. Now you can see that these two are identical, and we can identify it as this one. So remember yesterday I mentioned that layers are themselves are partitions. But if a graph in a layer is too large, you can further partition the graph into this one, and we use something called range-based partition, and here is an illustration of the range-based partition. What is range-based partition? So the nodes in the graph are numbered from 1 to 9, 1 to 10 here, 10. And we say 1 to 5 is in one partition, vertex IDs. 6 to 10 are in a different partition. So we also show that. So you can see that by partitioning it, you can see that some edges. So this is the adjacency matrix. So you can see here 5 has 1, 2, 3, 4, and 6 also has 2. So when you partition this, the edges that are on the partition will have their presence in both the adjacency list. So it preserves the adjacency information or connected information, and that property is made use of later for expansion and for what we want to do. So partitions are disjoint because they are range based. The reason we do disjoint partitioning is, given a node number, it's very easy to identify which partition it belongs to. We just hash it using a mod function, and then we can use that. Adjacency lists do not change between iterations. So our decoupling approach has 3 steps. Find substructures in each layer independently. Employ range-based partitioning for layers. So that is the first step, which is application of sign. Second, use composition function to generate interlayer substructures. So what the first step does is generate intra-layer substructures, that is substructures within the layer. The second step, which has been implemented, generates substructures across layers. And then the third step is to rank the generated layers, apply beam, apply MDL, and then go to the next iteration. So this is an iterative process. So we do the iterations till there is a stopping condition that determines the best substructure. So our decoupling based approach, the algorithm leverages homogeneous MLN property. Vertices in layers sharing the same IDs exhibit inherent characteristics. So in HOLMN, it is true that the node numbers are identical in both layers. Utilizes an iterative decoupling based method for substructure discovery within the homogeneous layers. And that is this one, this one, this one. Example of applying homogeneous substructure composition algorithm. SCA is substructure composition algorithm. So this is our initial aggregated graph. I'm just using the same graph. Here is the adjacency list for layer 1. Here is the adjacency list for layer 2. These are used for expansion. And now is the important step. Layer-wise output after iteration 3. So you have edges of size 4 at the end of iteration 3, because we start with, in iteration 1 you get edges of size 2, in iteration 2 you get edges of size 3. So you can see that on the left hand side you have substructures from each layer with the same colored edges. Now we take each of them and we split it into 1 edge, 2 edge and 3 edge substructures, and then we compose them into substructures from each of these things. And as a process, you can now generate, for example, from this substructure from layer 1, this substructure from layer 2, you can get this substructure. From this and this, you can, now you see what we get here is a substructure that spans both the layers. These have only orange and blue edges. These have both orange and blue edges. So this is how we construct this thing. Are you taking the exam as well? Huh? I think you should wait and take the exam. Otherwise, I don't have to do anything, you can just continue with the exam.
No, sir. We were just filling up the form we were supposed to fill.
Yeah. I mean, you can do it before the exam, otherwise you are going to miss out.
Okay.
There's no point in wasting time if you are engaged otherwise. This is for you, this is not for me. I know this already. I don't need to refresh myself again and again. I'm just trying to be honest. So, what is the challenge in substructure discovery? Existing approaches can be used to effectively discover substructures, but for each layer only. However, they will miss substructures existing across layers, and that is the whole point in this research. So, substructure discovery is an iterative algorithm. It starts with a single edge, all edges, expand each substructure by one edge at a time to obtain substructures of size 2 in first round, then from size 2, size 3 in the second round, so on and so forth. You have to, so we call it independent expansion because each substructure is expanded without the knowledge of what has been done before. So that generates duplicates, and you have to eliminate duplicates in each round, and that's where we use the canonical representation. So this is more of a theoretical observation or theoretical value. I hope you can understand it. Here is the spectrum of choices. On one of the y-axis we show accuracy, on one of the other y-axis we show efficiency. What it says is, because it's an iterative algorithm, when do I do this composition? I can do this composition after the first iteration, after the second iteration, after the third iteration, or after the last iteration. So I have a wide choice of when I should do it, but will I get the same result if I do it in different places? That is what this graph is trying to show. What it says is, if I do it at the last end, I get the best accuracy. If I do it at the end, I get the best accuracy, but my efficiency will be very low. If I do it somewhere in the first iteration, my accuracy will be low, my efficiency will be very high. Now, there has to be something called a sweet spot. In other words, there is a line where it intersects where accuracy is also high and efficiency is also low. This is what we call the sweet spot. So challenge is how frequently to perform composition, high accuracy, computationally expensive, higher response time, less accuracy, efficient computation, and better response time. So this is the trade-off. So there will be a sweet spot, and we don't know what it is. We don't know what K is. So we have not figured it out yet. We need to figure it out both theoretically and experimentally, show that what we come up with theoretically is also true experimentally for large data sets, and that will tell us if you are given a problem and if you have to do it, how to choose K. Depending upon the substructure size, you'll be able to choose K and do it in the best possible way. So contributions of this paper: MapReduce partitioned approach to substructure discovery in a layer, design and implementation of single composition algorithm for HYMLs to generate interlayer structures, determine the accuracy trade-off, extensive, parallel, and this experiments. So terminology is input graph representation, as I showed you, is a pi tuple. We use adjacency lists, we use independent expansion, we use one canonical representation for duplicate elimination, we use a slightly different canonical representation for isomorph detection. So again, this one gives you some example. If you are doing research, this is what you really need to do. You need to work on small examples to understand things clearly and then generalize it. So the algorithm is as follows. So the whole overall framework is take 2 layers. Now this need not be 2 layers. We are showing it for 2 layers, but it can be more than 2 layers. You do the expansion one by one, then you get a k plus 1 substructure during the expansion, so 1 to 2, and then next iteration 2 to 3. Then you apply the duplicate elimination, isomorphism, beam, and MDL, and then this is the analysis phase. So this goes back to iteration 2. So remember, in iteration 2, the input is not the original graph, the input is what comes out of this. So that's important to understand. Every arrow, every line has a significance here. If you don't show this arrow, that means your input is the same, it should be incorrect. Now, continuous still size k. Once it is all done, you get all the substructures for layer 1, all the substructures for layer 2. Now you do the composition algorithm on those substructures, and then you get the output and beam structures. So this is the general framework. Again, we have algorithms for parts of this. We are developing algorithm for composition, but still how to do it in a MapReduce framework is a different challenge. Because this does not say anything about MapReduce, this does not say anything about how to do this in the MapReduce framework. So the approach consists of 2 functions, analysis and composition. Analysis is performing substructure discovery, partial results are computed. So I won't go into the details of the algorithm. This is the algorithm for the composition function, not for analysis function, because this is what we have added. And when you present your algorithms, you should present it in a numbered line, so that in the thesis there are explanations for each line as to what it does, why it does, and why it is correct. Now let us come to the most important step. So this algorithm, both analysis and composition, is mapped into MapReduce framework, and that is how it comes out. Now this is the final solution, but coming to this final solution is not very straightforward. We have to go through a lot of iterations and figure out, and let me see how you can recognize a few things. You can recognize that there are 2 jobs, job 1, job 2. There are 2 jobs here also, job 1, job 2, and then there are 2 jobs here also. So you need a total of 3 different types of jobs. These 2 are identical. The data is different, but the jobs are identical. So these map tasks are the same. These map tasks are the same, these reduce tasks are but these map tasks are different, because what is fed here is the output of this one, and these map tasks are different. So finally for this one you have to develop 3 different, 1, 2, 3, 4 different map tasks, 4 different reduce tasks. And here are detailed explanation of what is. So this is what I force my students to develop for presenting the slides. All these are developed by the student. We go through a number of revisions to make sure it's clear, and somebody who does not know the problem can clearly understand it. Otherwise you can put a lot of stuff which nobody can understand. It's a waste of my time and it's a waste of your time. So typically what happens is these 2 are responsible for analysis. So this MapReduce combination expands, this MapReduce combination determines isomorphism and applies beam, and then this goes back to this one, and then same thing here. After all the iterations, the output, the final output after n iterations are fed to mapper jobs, and then here the composition takes place. And the composition takes place in the first job, and then MDL, beam representation, and determining which substructures take place in the second job, and you get the output. So, developing this architecture using the MapReduce is not straightforward, and it takes a lot of time and debugging and implementation and testing in order to make sure everything works correctly. So I hope you see the theory yesterday and its application today. If not all the details, but with this, if you're interested, you can go and read the thesis, or you can go and read the paper and understand it. So what is the experimental setup? All experiments performed using Java and Hadoop on San Diego Scientific Computer Expanse Cluster. So we don't have a very large Hadoop cluster at UTA. We have a small one. And so we use this facility that is supported by NSF. And this has 728 nodes. There are 64 cores per node and 128 built on 2 processors. Each node has 2 processors and 128 cores. It's an AMD architecture. Each node has 256 gigabytes of RAM, storage 1 terabyte Intel. So this is a fairly powerful capability. You can do a lot of computing using this. I don't know what kind of computing facilities you use in NIT Jalandhar, but if you want to do scalability experiments, if you want to do scalability work, then you need this kind of environment to test it out. Otherwise, it becomes very difficult to test it. So I was telling you, we do it on a very large data sets. So here are some of the data sets that are given here. So we started from small data sets for testing purposes. So synthetic data set to used for testing accuracy, response time, beam value, we use 4, 8 and 12. This is 2 maps and 2 reducers, 4 maps and 4 reducers, 8 mappers and 8. Synthetic large data set, larger than this. These are all for testing. Amazon is a real world data set, LiveJournal is a real world data set. Then we have a lot of synthetic data sets and real world data sets. 50,000 vertices, 100,000 edges. 100,000 edges, 500,000 edges. 400,000 edges, 1 million. 1 million, 4 million. This Amazon has 0.74 million and 2.6 million edges. LiveJournal has 4.9 million vertices and 69 million edges. And for each of them, we generate 3 cases. Layer 1, 50-50, layer 1, layer 2, 50-50 distribution, 70-30 distribution, and 90-10. So this is to show that it works for skewed layers, non-skewed layers, similar layers, uniformly distributed layers. This is very important. And this gives you an understanding of the number of edges. Because this is 50-50, it's more or less same. Here you can see that 70-30 means this is more, this is less, this is even more. So experiments were performed on a number of synthetic and real world data sets, varying sizes to establish. Subgen was used to generate synthetic graphs. For each data set, we further generated 2 layers. I don't know, it has its own mind. Okay, not okay. Can you push this one to see whether? Well, no, it's okay, I don't know. So this is the one that may be a loose connect, that one. Just jiggle it a little bit and see whether. Okay. So maybe it's giving us signals to wrap it up faster. This has nothing to do with that. It's either that end or this end. Is there another HDMI? No, that's the one. Is there another cable?
एक सेकंड केबल चेंज करिए.
Okay, so this is the data set, so you can see how many experiments. This is not the entire list of experiments. So here itself we can see 1, 2, 3, 4, 5, 6 into 3, 18 different experiments. Composition trade-off. So here is the graph that shows accuracy, and what it shows is that the size of the substructure, if you are looking for two substructures, you get 100% accuracy. In this method, if you go to 5 edge, it reduces because we are doing it at the end of all iterations. Remember that two graphs I showed you, this follows that graph. As the number of iterations before composition increases, the accuracy decreases. This is the important takeaway, and it matches the theoretical framework. Accuracy versus beam size. So we also wanted to test the accuracy, so we tested with 4, 8 and 12 beam size. So the expectation is when the beam size increases, accuracy increases, because this is a dynamic programming branch and bound algorithm, and that you can see very clearly for all the cases. As the beam size increases, the accuracy increases, especially for the 90-10, it's very high. 70-30, it's a little bit, 90-10, it's very high because one layer contains all the substructures or most of the substructures. So that dominates. That's why the accuracy is high. 50-50 is lowest because the substructures are split and they are not able to detect it. So this is intuitive understanding or analytical understanding matching with experimental accuracy. This is very important. Accuracy versus edge distribution, because we have 3 different edge distributions, we can also compute that. 50-50, 70-30, 90-10, again, it shows what we expected. 90-10 should show the highest accuracy with edge distribution, and that is shown for all the 3 cases. Speed up, so this is very important. This is for scalability. So what is speed up? You see here we have 8 mappers and 8 reducers, 16 mappers and 16 reducers, 32, 32, 64, 64. So we are increasing the parallelism. We are increasing the number of mappers and number of reducers. So what do you expect? You expect the response time to go down. And that is what you see here. This is the response time in seconds. So it drops 51%, 40%, 34%. Similarly this. So this is the scalability issue. By putting more resources, you are reducing the response time. Now why does it not reduce at the same rate? Why is this 51 and this is 40? So you also have to understand there is something called law of diminishing returns. Have you heard of that? Law of diminishing returns. This is not a computer science word, this is from business and marketing. Diminishing returns is if you put too many resources, if you try to flood the market, then the returns will not increase. If you control the market, then the returns are the maximum. The same thing is true because when you increase the number of mappers, the shuffle time increases. the overhead increases. The amount of work that is being done increases. These are known as overhead. So there is a overhead, double the overhead from 8 to 16, double 16 to 32, double, and that overhead cuts into your response time. That is why it's not a linear speed up. And if you go beyond that, it may even flatten out. It may not change at all. Here are some response time for all databases. We showed some 1, 2, 3, 4, 5, 6 into 4, and synthetic and real world. So these are all the data sets for which experiments were done. And again, presentation is very important. We have grouped them based upon the number of macros reducer is used. So you can see here in a different way how the response time is decreasing. And what you can see is it is consistently decreasing across the graphs. This is very important. It is not just it's happening for one graph, not happening for another graph, for the third graph. This shows that irrespective of the layer characteristic of the graph, you are getting the same or similar speed up. Now the last one is just to give a comparison of the subdue. I can't read it. Subdue, this is 100K, 500K, whereas these things go to millions of nodes and millions of edges, whereas this one is a very small. Still, its response time is very high because it's a main memory algorithm, no parallelism, nothing. So, to conclude, introduces a scalable algorithm, designed and implemented a single composite. He has also done iteration-wise, that is going to come out in a separate paper, and that has more accuracy results. So these are the people who worked on this. So what I'm going to do in the next 10-15 minutes, not take a lot of time, I want to show you this dashboard that we have done for this purpose, and we call it MLN-GWIS, a dashboard for supporting complete life cycle of complex data analysis. The important thing to understand is this, the joint effort with University of North Texas. Most of this dashboard has been developed by undergraduates. We use the Flash framework, we use Python, and we use Django, as I said earlier, and all other things. So let me first show you or take you to the website and show you a few things in case you get interested. So this is our website, IT Lab website, and as you can see that we have links to two dashboards. MLN-GWIS dashboard, which I'm going to show. This is the dashboard I showed you yesterday. We also conducted a series of lectures on multi-layer network. All the network lectures and the videos are there. The other thing you should see here is people. So we have a list of current alumni who are working, PhD students, MS thesis students, and so on. So all of them are listed here. Their thesis, whether it's a master's thesis or a PhD thesis. We also have people who have graduated. So this is a different list. This is a very long list. And we also have research, what kind of research we are doing, current projects. So we have information fusion using LLMs, that's a new project we have started, dashboard development, video situation monitoring. This is very interesting. If you like it, you can look. Big data analysis using graphs and past projects. Now, in addition to that, we also have a list of publications. Now, this lists all the publications that has come about from the IT lab over last year. So there are about 217 publications. And in the people, one thing I forgot to show you is for each person. So let's take, she's a new PhD student. So we put their name, once they graduate, we put their thesis. So let's take a look at somebody who has graduated. Let's say Soumya Das. Taking some time. So maybe pick somebody else. Looks like all of so he was one of my PhD students. Oh, why is this not coming? Oh, sorry. Okay. So he did PhD on stream data analysis, and actually we wrote a book after that. And as you can see, for every student, we put their thesis online. So you can look at the thesis and the topics, and if you are interested, you can open the thesis and read it. So for every student who has, okay, I need to go back. I need to go back. So here are the current students. He's a postdoc, and she's working on video monitoring. He's working on substructure discovery. She's working on weighted MLNs. These are undergraduates who are developing dashboards. Okay. So now, before I go into the dashboard, I want to show something here. Okay. So this is a dashboard we have developed for life cycle analysis. First, let us take a look at the poster. So this was presented in VLDB of this year, last month. I don't know whether you can see it. The poster is big, but this one comes out small. So I'm going to show, so this explains what this dashboard is, what kind of things we do, and here are some samples. This is the one I'll take through. And here is one. So this is a substructure that I showed you. I'm going to show in the dashboard. You can see in this small graph, orange has 4 edge substructures, blue has 3 edge substructures. And okay, so let's go to the dashboard. Oh, before that, we have made a 5-minute video, and it's also on YouTube. I think I may be playing it from the YouTube.
Welcome to the MLNG dashboard, a powerful web-based platform designed to simplify the analysis of complex data using multi-layer networks, or MLNs. Whether you're a researcher, data scientist, or analyst, this tool is here to help you model, analyze, and visualize intricate relationships in your data with ease. Let's dive in. Getting started is simple. Users can securely register and log in to access their personalized workspace. Each user has an independent workspace, ensuring their data and progress are saved
across sessions. This makes collaboration seamless and efficient. Let's go ahead and log in. Once logged in, you'll find the dashboard workflow for your reference. Let's take a look at the layout of the dashboard. You'll find the File Explorer on the left side. Here, you can organize and manage your data files. The dashboard supports raw data sets in CSV file formats. Uploads are currently disabled due to security concerns, but don't worry, we've preloaded sample datasets for you to explore. To generate MLN layers, you'll use configuration files with a .gen extension. These files allow you to specify how layers are created using various similarity metrics like Euclidean, Haversine, or Jacquard distance. Once generated, layers are stored in your workspace for further analysis. Next, you can analyze your layers using configuration files with a .ana extension. For example, let's analyze our dataset of traffic accidents in the UK. Let's discover communities of accidents that took place within a 10-kilometer radius of one another. We can also further group them by the radius combined with the light condition at the time of the accident. The dashboard integrates community detection algorithms like Louvain and Infomap, as well as homogeneous MLN algorithms developed by us, enabling you to detect communities, centralities, and substructures efficiently. Our innovative decoupling-based approach streamlines the analysis process, making it easier and more effective. One of the standout features of the MLN GWiz dashboard is its interactive visualizations. You can explore your data through dynamic network visualizations, community-based color-coded graphs, and even geographical maps. Let's continue with our UK traffic accident example and visualize the communities we've discovered through our analysis. We can view a word cloud visualization, which allows us to understand the size of each community, with community labels being proportional to their size. We can also view a community network visualization to view a graphical representation of the communities we've uncovered. In this case, each group of nodes is color-coded and grouped based upon its location, which we previously defined to be a 10-kilometer radius, as well as the light condition at the time of the accident. The drill-down capabilities of the visualization alternatives can be highlighted here if we hover over nodes. By hovering, we can view important information about the nodes. We can also click nodes to view the precise location where the accident took place on the real-world map. If, for example, you'd like the threshold to be lowered and the accidents be grouped based on closer proximities, threshold can simply be lowered in the layer generation file and regenerated, and the new layers can be reanalyzed and visualized. We also have more visualization alternatives, allowing for easy visualization of layers before they're analyzed. These include network visualization, interactive visualization, community visualization with drill down, and degree centrality with drill down. We also have a map visualization available now on our airline and flight dataset. The MLN GWIS dashboard is built with a modular architecture, making it easy to extend and add new features. Whether it's new analysis algorithms, visualization options, or data sharing capabilities, the platform is designed to be extended. The dashboard is a powerful tool helpful in unlocking deeper insights from your complex data. Whether you're studying social networks, transportation systems, or searching for patterns in data, this platform provides a new way to model, analyze, and visualize your data. If you'd like to explore the dashboard yourself, visit us at itlab.uta.edu. Thanks for watching.
Okay, so that is the 5-minute video we had to do for submitting the paper. This was also done by the students. So I'll just spend a few minutes to show you some of the things that you saw in the live. So this is a publicly available dashboard. You can go to that link, go there and log in and then do whatever you want that it allows you to play with. So I would really appreciate if you play with it, see what you like, what you don't like, send us feedback. There is also a contact us button that will allow, and the dashboard demo is also there. So let me see whether I can go. So this is a flowchart we are given for new people. So it just takes you walk through, if you're done with the dashboard, provide feedback and log out. Otherwise, select an application, select .gen files to generate layers, select .ana files to do analysis, and then visualize. So these are the different steps we do. So here is what you see when you go into the dashboard. There is a logout button, there is a profile button, and you just have to give your email in order to log in, and that is the only thing we need, and then you come back and use the same password and log in. So let me first start with the substructure discovery that we are talking about. Remember, we talked about layer characteristics. So we have generated a few layer characteristics to show you. This is so anytime you see a file, if you click on that, you will get the contents of that file. So this is the layer characteristic for the 100 node 200 edge file. As we said, it says 100 nodes, 200 edges, density, number of connected components, max degree, average degree, standard deviation of the degree, min weight. If you have weighted graph, it will also show you min and max weight, percentage overlap edges, because this is similarly we have one for a smaller graph which is 16 and 20 node, and that's what it is. So that's one thing. Now for the graph I showed, we have run the substructure discovery, and here are examples of 4 edge, substructure discovery. Now, when you click, when I click on, so notice that visualize button is on. When I click on this one, visualization button is off. So what it means is, if you can do an operation, that operation will automatically come up, depending upon the extension of the file. If you cannot do the operation, that won't come up. So that means you cannot visualize this file, but you can visualize this file. And you can visualize in so many different ways. You can visualize, interactive visualization is good. So this will shows you the two 4-edge substructures. The labels are missing in this one. And this is so you can run the substructure discovery algorithm, get the result, and see that for a small graph, it's easy to do that. You can also visualize it in this one, which is slightly different from there. You cannot move things around, whereas here, you can interact with this graph, push them around, move them around, and do that. So this is what it is. So now let us go to the accident, and then if I have time, I'll show you. So in the accident database, I told you, so we have data files. So just to look at the 500 UK accident, 100 UK accident, which is a CSV file. So this shows you the raw data file that we use for analysis. This is a CSV file. You cannot visualize it, you can just look at the file, you can see all the file, part of the file, some of the files, you can also look at the log. Now, this gen file is our configuration file where you specify how the layers are generated. So it says, for example, begin layer, and there is an end layer, which generates one layer. You can generate multiple layers in that. There is also the analysis file, which is a configuration file, where you say begin analysis, end analysis. You can see AND-based multi-layer communities. So you just say, I want to compute accidents within 10 kilometers, and then I want to compute it for 2 layers, and then I want to compute communities using C and. So you can do those kind of analysis. So that we have some analyzed results. So when you do that, they go into the appropriate folders, and here are some that I would like to show. So he said, my student yesterday said, well, there are a lot of them. Light condition. Okay, so ecom is the community file that includes edges. vcom is a community file that only has nodes. So if I pick this file, you will see that visualization automatically gets on, and you can visualize it as a community bar chart. So you can say, what are the communities that have been generated in this analysis? In this case, there are only 5 communities. These are the number of edges, these are the number of communities. You can also look at as a word cloud, and you will see that there are only 5, the same 5, C5 being the largest and the others. The interesting thing is to do the drill down. Here you can see the communities individually. Maybe this. Okay, so Okay, let me. So when you click on a node, it takes you to the actual location in UK, where that intersection is, where that node is determined as the node for that intersection, and you can look at it. So this is the, I don't understand the UK things very well, but you can see, and if you want, then it gives you lat long, and if you want, you can do the road view of that particular thing. So this is what I was calling about drill down and visualization. This drill down and visualization is important from an analysis point of view, because somebody, a politician or an administrator who is making a decision, it is not enough if you give them lat long. They want to know where it is. They want to know how it looks like. So you need to provide this level of visualization if you want to do something. So let me see, can I go back to my dashboard? Yeah. So let me, there was one accident, same road surface, accident. So these are different layers we have generated. We have done different analysis. This is the day of the week. This is the one that does the 10K. Oh, this only has word cloud. Oh, sorry, this is ecom file. Sim surface. Accidents within 10 ecom. So this may have my more community. Yeah, so you see here there are a lot more communities that are developed for this particular analysis, and then now you can zoom into a particular community. These are all the nodes that have the same type of accident under the same conditions that are within 10 miles radius, and it will give you the node ID. If I click on one of them, again it will take you to that particular location and the intersection where the accident is. So this has been merged with Google Map and other thing. Okay, so let me go back and show one more thing and stop it, because you guys are waiting to do the exam. You're eager to do the exam, or you're eager for the tea, I don't know. My goodness, so something happened here. Okay, so let me close these things and just go back. Well, something is, it was working and something is not with the server. So I'm not sure exactly what it is, whether this is an issue with this one. It says it is connected. Let me okay. Let me try and, no, it's not happening, I don't know why. So, let me see whether this one is working. This one seems to be working. Taking a long time. I don't know what the issue is. So I just want to show you one more thing in the airlines and then stop. So we have all the different airlines and layers generated for different airlines. So, oops. one is now. Okay, I'm going to start it. So you can play with it. It's working, the live is on, and I'm not sure what exactly is happening. We use Nginx and reverse proxy for doing a lot of stuff. So let me conclude and summarize this course. So thank you for registering and attending the course. Thanks to NIT Jalandhar and Professor Bansal for taking effort to organize this course. It has been going on for almost 2 years. It has not been easy, but I want to emphasize is, we have tried to give you a feel for what data analysis is, right from starting with understanding of data, various ways we manage and store data, initial work on data mining, now more recently big data, cloud computing, graph analysis, multi-layer network analysis, scalability using MapReduce, and also hands-on experiments to do various real-world data sets. I sincerely hope this has given you some understanding, and from now onwards you can take it on your own, either for your research or for your work or your career, and I hope you benefit from this. Thank you so much, and I would like to conclude this course.